And what that does is it depends on, it assumes that everybody has a fixed number of encounters per unit time. So in other words, it's like a satiation phenomena where you don't contact 100 people a day, you just contact 10, no matter what the density is out there. And so that's the case for sexually transmitted diseases, is the frequency that you have sex with strangers doesn't go up with the density of the people, I hope. But it could. So then for a frequency-dependent process, if I'm going to have 10 encounters a day or 20 encounters a day with people, what's important is what proportion of those individuals are infected. So if 10% of the population are at this time infected with influenza, and I meet 20 a day, then the expected number that I will meet with influenza will be 2. Unless they actually, if you get influenza, you stay home and you don't go out and meet people. So one can have lambda being frequency-dependent transmission or mass action or density-dependent transmission, as they call it. Now we're just going to assume a very simple density-dependent transmission, and this term is often called beta SI. So it says the rate at which the disease is going to spread is proportional to the number of susceptibles and the number infected in the population. Imagine kids playing on a playground, and the denser the kids are on the playground, the more individuals they make contact with. And the number of contacts is proportional of potentially infectious contact is proportional to S times I. So as the proportion of infecteds goes up, you're going to increase the rate at which transmission happens. But beta then is a parameter that tells you how transmissible the disease is. So for example, Ebola is actually a very difficult to transmit disease. Fortunately, if you think about, well, compared to things like measles and compared to influenza. So beta must be lower for some diseases like Ebola and much higher for things like measles. Now what happens is the rate at which susceptibles become infected is proportional to beta SI. So this is the rate of change of S. S is decreasing because fewer and fewer individuals, the susceptible population is growing smaller as they transfer from susceptible to infected. So it's negative because we're looking at this process of S is leaving S and going into I. So it's negative as you leave S and positive as you go into I. And then I grows as individuals become infected, so the infectious class is growing. And then individuals are leaving the infectious class at an exponential decay rate. So what it says is that if I took a population and 100 people in the room had influenza, there would be a rate so that in 2 days maybe a third have recovered, and 2 days later another third. And so it would be an exponential recovery rate. So the number of infectious people would go down exponentially if there weren't any new ones coming in. Is that a reasonable assumption? Who thinks it's reasonable? Well, it's the first assumption, but what would you do maybe to try and modify that? What are things that sound unreasonable about that? Beg your pardon? Right, so there's individual heterogeneity, but let's say every individual did have the same recovery rate. Would you expect it to be an exponential process? What would you expect? Well, you'd expect a natural, so if I become infected and you become infected, we would all expect to recover around the same time or die around the same time. It's like if you get Ebola, it's not like you get Ebola today and some are better tomorrow and some are better on the next day. And usually what happens is there's a period of about a week where it's not clear whether you're going to make it or not, and then you either make it or you don't. So it's kind of a fixed period. So these models really strongly idealize the process. And so they don't take into account whether I've had it for 1 day or 2 days or 3 days or 4 days, which in a natural disease process is important. And it's the same with individuals who are exposed. If you've been exposed to the disease, you can't say a certain proportion will be infectious tomorrow and another proportion infectious the next day, and that'll be an exponential process. No, it's kind of like there's a fixed period where the disease is doing its work at low levels, it's getting into different parts of your body, it's establishing itself, and then it makes a big growth spurt, and then you become ill. So that's called the latent period. So from the time you get infected to the time you become infectious, you're in this E class, it's called the latent period, and you expect that period is more likely a fixed period than an exponentially changing time period for people. So these are approximations. So now in this particular model, it says, if we make beta equal to 1, analyze the behavior of the system for the case r equal to 1/2 and for the case r equal to 1.5. So if we make beta equal to 1, then you'll see that that's just, it's actually, you can always make beta equal to 1 without loss of generality, because I haven't told you whether the time period is a day or an hour. So you can always choose the time. So the value for beta can be scaled so that it's 1, and then you have to find what's the appropriate time period you're working with that would make beta 1. But once you've done that, then the value of r relative to beta becomes important. So what's important in the dynamics of this population is the relative value of beta to r. Now if you notice, when r is equal to 1/2, that if you started off with a population of susceptibles, so that you normalize your susceptible population to be 1 unit, and I was rather small, if r is smaller than beta, then the epidemic is not really going to do anything because, then the epidemic's going to grow, and then eventually it'll come down again. You'll see the dynamics. If r is too big, then individuals are recovering too fast, and so the epidemic can't get going. And so you expect 2 cases to arise, and let's see, in fact, what happens. So when you get something like this, you're going to say, I'm going to do a null-Klein analysis. Now, you might say, how can I do a null-Klein analysis? Because I've got 3 equations. I can only do a null-Klein analysis if I've got 2 equations. Well, it turns out that if I make the assumption that S plus I plus R is equal to the total number of kids in the school, then it means that the total number is fixed at n. I've got a school of 600 kids. I've got a process coming through. I want to see what happens. So when S and I and R are linked to a total number, then you can say S plus I plus R, as I do over here, is equal to 1, okay? And which means that R is equal to 1 minus S minus I. So if you just look at the first 2 equations, firstly, R doesn't even appear in the first 2 equations, so you can do a phase plane analysis on just these two equations, S and I. But you can also make the assumption that R is equal to 1 minus S minus I, which would help you get rid of that equation. But to begin with, we can just take the null lines for S and I for the first two equations. So there are two cases when you do this phase plane analysis. The first case is when R is equal to a half, and you draw the null isoclines. If you set S and I to, if you set N equal to 1, in other words, 1 unit, so this 1 unit might represent one school, may represent 100 individuals, but it also could represent the proportion of individuals that are susceptible, the proportion that are infected, and the proportion that are recovered. If you do that, you only have to look what happens in the phase plane between 0 and 1, because S cannot be bigger than 1 and I cannot be bigger than 1 if they're proportions. So you do that, and in the first case, when R is equal to a half, you get an isocline over here where I is not changing, but only S is, and you can show from the arrows that you draw that if you start out with S very close to 1 and I very close to 0, which is like saying, we've got 1,000 kids in the school, and one of them comes in with an influenza, or one of them comes in with a cold, is it going to spread? So you're starting out very close to 0, 1 in terms of the proportion. Then you can show that it'll grow, it'll cross here vertically, and then it'll come down. And where it comes down, we can call that S infinity. So you can solve the equations, the differential equations, goes up, comes down, and it asymptotically approaches S infinity. Now what you're able to show in this analysis, and the analysis is in here, but you can just go through it if you want to go through it. The other way to do this is just to build an over model and to solve this from different points. And you'll see that if you start out in slightly different places, you'll come to different values. Finally, you'll approach different points. That point is what proportion of individuals got the disease. So if you look at a disease process, a strange thing happens. You're in the school, and people are beginning to get sick. And then eventually, because it's a finite number of individuals, it can't be asymptotic. But after a certain amount of time, the disease is now gone, and it may be that 1/3 of the individuals never got it. So why does that happen? What was special about the 1/3? Well, it turns out that it's just a random effect. And what happens is as more and more individuals get it, so there are fewer and fewer susceptible individuals that can potentially get it. And eventually the disease starts to run out because mostly infectious individuals are meeting each other. And susceptible individuals are meeting susceptibles less often. And more than that, they're running out of susceptible individuals because infectious individuals are going back to being R and not to being S. In other words, after you've had the disease, you don't go back to being S, you go back to R, and now you can't get the disease. So now lots of I's are moving around, and they're no longer meeting S's, but they're meeting R's, and they can't transmit the disease to R. So in the end, the disease runs out because there's sufficiently many R's in the population, and some of the I's are now meeting R's instead of S's, and that doesn't lead anywhere to new infections. That's only for an SIR process. For an SIS process, it just keeps going, individuals. So that's why gonorrhea epidemics just keep going, and there's a certain number of individuals that have it at any time. In order to get, it can go away naturally, you can recover, or you can go and be treated for it, but it just keeps going, whereas something like influenza, you have a start and an end. And if R is too big, then if you've got a very low level, if this is little r, not big R, if this rate at which individuals recover is too fast, then when you start out with very few individuals, it keeps just going straight down. It doesn't go through a growth period and then go down. So here you have a situation where the disease will automatically just fade out. So you get a bunch of people coming in, maybe some will get sick, 1 or 2, but then it'll fade out. And in fact, Ebola was like that. There would be a few cases, but it would fade out. There would be a few cases, fade out. Then there would be a few cases, and it would grow, and it would fade out. Now, this is the first time that there's been a massive epidemic. So what's changed? You can say what's changed is maybe the density of the population is now more dense. But also, in this model, where we assume mass action, you assume perfect mixing of everybody with everybody else. In a real situation, you have people living in little villages, and they're not mixing on a big scale. So you can get a local epidemic in a small village, and then it burns out. But if there's somebody infected there and they start moving around, then they're mixing the population. So it's not clear why Ebola really had this big outbreak recently, but I would speculate it's affected population densities. Densities in countries now are doubling probably every 20 or 25 years. And also people are moving around, so it's those two phenomena. So you can look more closely at this example, and those of you who are mathematically inclined can find out how to calculate S infinity as a function of the initial S0, or S0 are the proportion of susceptibles, which may be 99.9% or whatever that number is, and it also depends on little r. If you notice, solving this equation where you've got S infinity on this side and S infinity on that side, it's not a simple linear equation or a polynomial equation, it's called a transcendental equation. You can't just solve it directly. But you can get a relationship where you draw two curves and you can see where the solution is. And now you can use your calculators to do that as well. So we're not going to talk much about that. If you come to a pure SIS model, so in an SIS model, what's happening is susceptibles are becoming infected, but infected are recovering at a rate R back to susceptibles. They're not recovering. In the previous model, the RI term was in a third equation. Now it's back in the first equation. So this term now is back in the first equation. And now you can use the fact that the number of susceptibles plus the number of infected individuals is equal to the initial number in the population, and if that's not changing with time, in other words, if individuals not dying, so this is a disease that's not killing people, but some people at any time are infected and some are not, then you can say what proportion will become infected and what would the population look like. And so you can say n is equal to s plus I. If n is equal to s plus I, then dn dt is equal to ds dt plus di dt. But if n is a constant, that's equal to 0. So that allows you to say s is equal to the initial number of individuals minus the number that are infected. So if you go to the I equation, and where you've got s, you put n0 minus I, you can show that this is a logistic equation. So you can go through the math. So this is something you should know how to do. I mean, I could say in the final exam, if you take this particular equation over here, and you make the assumption that n is equal to s plus I is a constant, show that this gives you a logistic equation and derive that logistic equation. Would that be too horrible for an exam? Okay, so what happens is I take this equation, didt equals beta is minus ri, where I've got s, well, I first take I out as a common factor. And then I get this equation where I've got s in this equation, I replace it, where I've got this s, I replace it with n0 minus I. So so then I can show that the IDT satisfies this equation. Now, if I take an equation like this, I say, is this a logistic equation? Yes, it's a logistic equation, but it doesn't quite look like a logistic equation. Here's a constant. There's a constant. So what I want to do is I want to divide out by beta n0 minus r. I want to take it out as a common factor, which means if I take it out, I'm left with 1 over here. So I take that out as a factor, which means that this term becomes 1, and that this term becomes beta divided by the factor that I take out. Now I've got something that looks like my logistic equation, where this is the constant a, for example, in the logistic. And this thing here is 1 over the carrying capacity. And so it's a logistic equation, and provided beta n0 minus r is positive, then it's a logistic equation. If this is not positive, it can't be a logistic equation. In order to be positive, it's required that n0 must be greater than r upon beta. This r upon beta is called a threshold. So what it tells you is that in order for the population, the epidemic to invade, there must be a threshold density. So with this kind of model, it says if the population is not dense enough, the disease can't invade. When it becomes denser, then the disease can invade. So this is one of the reasons why diseases are becoming more common, is because we do live at higher densities, and we do contact other people more often. And we do go and sit in we do go and sit in trains, and we do go to the cinema, and we do go to concerts, and we do have huge numbers of people around us close enough that if they cough, it's possible that we can inhale the viruses that they're coughing. I know this sounds awful, but every one of us at this time is exchanging molecules of oxygen and carbon dioxide and so on. Everyone's breathing stuff out and breathing stuff in, and we're sharing all of this. Yep. Well, so animals that are not social have fewer problems with parasites and that sort of thing. So, yeah, social animals are more conducive to maintaining populations of parasites. Now, there are pathogens that are generalists. So like anthrax, so you don't have to have a high population of zebra, and you could have a single zebra walking around, and as long as there's other kinds of antelope that are maintaining the anthrax, that individual is susceptible because anthrax is a generalist. But things like HIV are very specific to human, although there are related viruses like SIV. And so it's thought that HIV did come from various monkeys, and there are two strains, one from chimps and one from mangabey monkeys, and that it took a mutation of the strains to adapt to humans and to become successful in humans. But in general, social animals do have diseases. So, for example, one of the reasons for animals to move around, like they live in burrows, they abandon those burrows every few weeks. Hyenas may do this, some of these ground squirrels may do that, and it's thought, like leave the parasites behind, try and go to a new fresh place. Yeah, so solitary animals are more successful from that point of view, but they're less successful from other points of view. So that's where the trade-off comes in life history. So now we can come to what I have called an SIVS model, but it's just an SIRS model. I don't like the designation R because it means two things. It means removed, but it can be either you're removed because you're immune or removed because you're dead. So sometimes if you want to make a more sophisticated model, you have to take the R category and break it into two. So I call them V and D. V are those who are vaccinated. Now I don't mean they were out and vaccinated. This is kind of a natural immunization. So they're those that are immunized because they got the disease or because they were vaccinated. But we can't call it I for immunized, so I call it V for vaccinated. So this is an SIRS model. So what happens is that there's recovery of individuals from the immunity. They lose their immunity and they become susceptible. And the I's go over at a certain rate to being immune. And so you go from S to I, to having immunity, to losing your immunity and going back to S. Now, in order to model this, you've got 1, 2, 3 equations. If you want to use a phase plane analysis, you have to get rid of one equation. One of the ways to get rid of an equation is to use the assumption that S plus I plus V is a fixed number of individuals. Now, obviously, if individuals are also dying, you can say S plus I plus V plus D is a fixed number of individuals, as long as you count everybody who's above the ground and everybody who's below the ground. When it becomes a variable number of individuals is when S's come into the population, and they can come in two ways. They can either come in through migration, or they can come in through births. So if it's a long-term disease, where you want to have a look at what the disease is doing over many generations of the host, then you have to have the host demography in there. You have to have the births and deaths of the host. If it's a very fast disease, then you can say, like, I've got a fixed population. It's like an army barracks, or it's a school, or it's a town where the number of births that are going to happen in any 1 year is just a small fraction of the total population. So the total population size, because of demography, over the course of disease, may change by less than 1%. So then I can assume, well, there's a constant number of individuals, and these individuals are turned from S's into I's and V's and D's. And then I can get rid of one equation. So if I get rid of one equation using that assumption, then I get